To start, we're going to do section 4.2 today, which we're really almost done with 4.2 already. So we finished most of 4.2 last time, and we'll go ahead and finish it up today. We'll spend some time working some problems, but we'll also get well into 4.3, and what that does is lets us have most of the class period on Friday to do some more unusual type problems and practice a lot of problems. Okay, so I'm going to do that a lot today. Make sure you have your calculator out and you have some paper you can work some problems on. And I'm going to have you work problems I'm going to come around and look at. All right? Okay, so to start this off, I want to work some problems based on contingency tables. And so I made a few contingency tables from analyzing the data that you guys sent in. So we're going to start with this one, which is a contingency table. I'm not sure if you've had that term in here yet or not, but a contingency table is what we call a cross tabulation of two categorical variables. So what do you think that means, cross tabulation? We did frequency tables, but each of those frequency tables only had one variable in it at a time. So we did one on the exam that had a frequency table for heart rate broken down into classes, right? But a contingency table does a cross tabulation of two variables. So it is just a frequency table, but the numbers in the table are the frequency of people that meet both conditions, right? So what we're looking at here is smoking by exercise. So the software that I use makes this a little bit hard to see what it's doing, but the word smoke is above this column. So these are non-smokers and these are smokers, right? Everybody understand? So then exercise is written over these two columns. So this is no for exercise and yes for exercise. Right? So these 218 people are exercisers. These 39 people are smokers. Right? So it's a cross tabulation. You can not only tell what percent of people smoke, what percent of people exercise, but you can tell people that do both. Or do one, not the other, that sort of thing. Okay? So it's called a cross tabulation. So let's start with some probabilities based on a contingency table. Let's define events with the capital letter like you're used to doing. So S for smoking, E for exercise. Got it? So what is the probability that a randomly selected person from these 365 people, what's the probability that that person is a smoker? I tell you what, because it's not showing up on the camera, I'm going to copy that table down here. I can't get it to go lower, but we have smoke, yes, or it's no, then yes. And then we have exercise, and it's no, then yes. So in this table, we have 120, 206, 27, and 12. And then out here, we put the totals. So the row total for non-smokers is 326. The row total for smokers is 39. And so on. And then 147 for the number of non-exercisers, 218 for the number of exercisers. And a grand total of 365. And this number down in the very bottom right corner of a contingency table is called the grand total. So you have row totals, you have column totals, and you have the grand total. Right? So this particular table is a 2 by 2 table. What does that mean, you think? 2 by 2.
2 across, 2 down.
Yeah, 2 variables.
Okay? It has 2 rows and 2 columns. 2 across, 2 down. Right? So we will always put the dimensions in that order, row by column. Okay? Now, you might look at this and say, well, wait a minute, I'm seeing 3 rows of numbers and 3 columns of numbers, but the totals don't count. They're not part of the table, so they're in what we call the margins of the table. So when we do probabilities that deal with marginal totals, they're called marginal probabilities. All right, so now we have that all laid out. Let's come back to this. What is the probability that a randomly selected person from among one of these 365, what's the probability that person is a smoker?
39 out of 360.
Good, 39 out of 365. Give me that as a decimal.
9.358.
What?
Not, oh, never mind. Right.
107.
Point
107.
10, give me 4 places.
106.
1068. Okay? I just by habit I like to keep 4 decimal places for probabilities. Okay? All right, so what's the probability that somebody is an exerciser? You do that. I have to stand where the camera will stay on the numbers. Probability that somebody from among these 365 is randomly selected and it turns out that they exercise. What 2 numbers do we divide?
218.
218 by 365, and then as a decimal?
0.5972.
5972.
3 added.
Okay? So then when you look at these numbers, you can say, well, a little more than 10% of people smoke. And right almost 60% of people said they exercise. Okay, now, let's make this a little harder. Probability that they smoke or they exercise. So I randomly select one person from these 365. What's the probability they're either a smoker or an exerciser? I want you to work this problem. We did this rule at the end of class last time. You work this problem, and I'm going to walk around and see how you do. Instead of letting the camera follow me around, I'm going to keep it pointing at the numbers. Okay, you're partway there, but let me ask you this. Among these 257 people, are there anybody that is counted at both times? If you heard me talking to Adam, you'd have to worry about people that are both, right? People that both smoke and they exercise are going to screw this up. No, that's an and. You guys, it was like an obstacle course getting around. And
Let's see. I gotta redo it.
okay, one of the things that makes people not like mathematics and statistics classes is because I can't memorize all the formulas. But a little bit of common sense, right? A little bit of common sense. Look at this, at the numbers in the table. I got 4 numbers here. Which ones of those 4 numbers meet at least one or both of those conditions? They either smoke or they exercise, or both. What about these people? No? What about these people? So there are 206 people who don't smoke, but they do exercise, right? So I'm just going to circle that number. What about these 27 people? Yeah, they are a smoker. They don't exercise, but they do smoke. So they satisfy the S part of this, right? So circle that. What about these 12 people? They satisfy both conditions. They both smoke and they exercise, right? So if I add those 3 numbers together, divide by 365, I have my answer. But I can do it probably easier if you already have these. What is the addition rule? Probability of S plus probability of E but among these smokers, look at this 39. This 39 was the sum of these 2 numbers, right? And then the 218 is the sum of these 2 numbers. Who gets double counted?
The ones that just,
The ones that satisfy both conditions, these 12 people. So the addition rule, you can sum the 2 probabilities, but then you must subtract off anybody who meets both. Right? So then that is 39 out of 365 plus 218 out of 365 minus 12 out of 365. Give me that as a fraction and then as a decimal. Everybody have that summed up? 245. 245 out of 265. 365, thank you. Yeah, 245 out of 365. And that as a decimal is? I heard too many numbers all at once. What?
0.6712.
0.6712. Okay. So 67% of the people are either a smoker or they exercise. Okay? This is called the what rule? The addition rule. Right? Yeah.
Could you also use the complement somehow?
You sure could. What did you notice here?
Well, that complement, which is neither smoking nor exercise. It's not.
Yeah, we don't go that far in this class, but there's rules of set theory and probability theory where the complement of an or is the and of the complements. So the complement of smoking or exercising is they don't do either, right? They don't smoke and they don't exercise. That'd be S complement and E complement. And when you see it like this, it makes it real obvious. That would be 120 out of 365. So then I could do the complementary rule and say, well, and it's just 1 minus 120 over 365. And notice that if I take 365 minus 120, I get 245. So sometimes it's easier to do the complement. Okay? All right, well, I don't have it so that I can project it on the screen right now, but I'm going to read you a problem, and I'm going to copy the numbers down as I read them, and then I want you to work this. But this is out of the homework on page 212 of the book. Oh, trying to juggle too much. I lost my page. What did I say, 212? Number 23. It says a flight attendant for USA Airlines is given an assignment that is randomly chosen from the following available flights. So they have all these different flights that they're flying, and they randomly assign them to the flight attendants, apparently. Right? So, well, let's see. It says, of those flights, there are 15 European destinations. So 15 European destinations. There are 6 Caribbean destinations. There are 8 South American, 5 Asian, and 11 domestic. So USA, within the USA. Okay? So there's the numbers. Then it says, what is the probability that her next assignment takes her either to Europe or Asia? Probability either Europe or Asia. Okay, work that probability. Say it again.
What's the What's the sex?
Caribbean.
Caribbean. Now, while you're doing this, you wouldn't have to do this, but it helps, I think, if you learn how to organize your information. So write it using notation like this. Use single letters for events. Since they all start with a different letter, that'll be easy. Right? And then write it, probability of either Europe or Asia. Write that as a probability statement. It helps you figure out, okay, what rule should I be using here? Okay? And I'll come around and look at those. You got an answer? Okay, good, that's right. Good. Good. You guys are getting it faster than I can get down the aisle. That is right. It's not there yet. You haven't there. Ooh, nope. You have it. 245. Yes.
No, oops.
Yep. Okay, is everybody getting .444 repeating? Right, so if you add them up, how many total flights are there?
45.
45. And then of the ones that meet the conditions,
20.
that's Asia and Europe. So it's 20 out of 45. So you don't really need any fancy schmancy rule to do it. But I want to use the rule because there's something interesting that happens. Probability of Europe or Asia, E or A. By the addition rule, that's the probability of Europe plus the probability of Asia minus the probability of Europe and Asia. Okay? What's the probability of Europe? 15 out of 45. What's the probability of Asia? 5 out of 45. What's the probability that one flight is both a European flight and an Asian flight?
0.
0. It can't happen. So they are called mutually exclusive. Right? So mutually exclusive events that means that they cannot happen at the same time. So I'm going to say cannot both occur. So the way we write that with probability statements is the probability of A and B is 0. Right? So I didn't introduce A and B up here. Mutually exclusive So I'll say A and B, events, any generic events A and B. They're mutually exclusive if the probability of their happening at the same time is 0. So the book gives us 2 addition rules. This one and then one without that piece for mutually exclusive events. But you don't really need 2. You only need this one because if they are mutually exclusive, then that's going to be 0 anyway. So you're not subtracting anything off. Right? So let's go ahead and finish this out. That's 20 out of 45, which is 0.44 repeating. Okay? Pretty easy, right? All right, now let's come back over here to our contingency table with smokers and exercisers. What is the probability of smoke and exercise? This time it's an and statement, not an or statement. Oops, I forgot. I know what you're thinking. You're thinking, didn't we already do this one? Did we do this one? Yeah. Probability of smoke and exercise, we said was 12 over 365. So if you have a contingency table, then again, you don't really need any fancy rule to do it. Right? The probability of an and is the number of cases that satisfy both conditions divided by the total number of cases. But it's not always so simple. It's not always in a contingency table where it's easy. So we need some rules. So the and rule is called the multiplication rule. And before we can do the multiplication rule, I need to introduce a new topic, or a new term, and that is independent events. Okay? Independent. What does that word sound like it should mean? What's that?
Separate.
Separate. Okay, they can be separate, and they would be independent, but it can be even. They don't have to be separate. If two. Let me start that sentence over. If one event occurring does not influence, that's the book's word, influence. If one event occurring does not influence, and I'm going to put in parentheses, change the probability of the second occurring, they are independent.
So it does not rely on something else.
Right, exactly. It does not rely on it. All right, so here's an example. Okay? I got a deck of cards here. Okay? If I shuffle this deck, and I have Adam here, draw a card, any card you want. No, not that. Just kidding. All right? What's the probability that Adam just drew an ace? 4 out of 52. There's 52 cards in a regular deck, and 4 of them are aces. Right? Now, Mariah. Draw a card, any card. Okay. What's the probability Mariah just drew an ace?
4 out of 53.
3 out of 15.
4 out of 53. We added a card?
Oh, wait, yeah, no, the other way.
I'm just kidding. 4 out of 51? You sure?
Unless you drew an ace. Unless you just-
What did you say?
Unless you drew an ace.
Okay.
We don't know.
We don't know, right? So what is her probability? Just answer the dang question.
Don't know.
We don't know.
It's dependent on what Adam drew.
What did you say?
It's dependent on the card that Adam drew.
It depends on what Adam drew. Definition of independent events. If it depends on the outcome of the other one, then they're definitely not independent events. They're dependent. Because the outcome of his draw influences the probability of her draw. If he's holding an ace, what's her probability?
3 out of 51.
3 out of 51 cards that are left. If he's not holding an ace, are you holding an ace? He didn't get an ace. So now what's her probability? 4 out of 51, because all 4 aces are still in the deck. So if one event influences the probability of the next event, they are dependent events. All right? Go ahead and put your card back. Put yours back. And I reshuffle. Okay, they're shuffled, because it doesn't really influence this problem. Right? Now, he draws a card, looks at it, puts it back, and I reshuffle. What's his probability you got an ace? 4 out of 52. Now Mariah draws a card. You get an ace? Still no aces. Oh, Wagner. What's her probability of drawing an ace?
4 out of 52.
4 out of 52. Why is it 4 out of 52 this time? Because we put the card back. Right? So that is the difference. It's called sampling with replacement or sampling without replacement. The first time we did it, we sampled without replacement. He drew his card, kept it. She drew a card. That's sampling without replacement. If you sample with replacement, you get independent events because the probability didn't change. Right? So, sampling with replacement leads to, an arrow, leads to independent events. Sampling without replacement this ditto means replacement, leads to dependent events. Now when we draw sample surveys, if we're doing research, it's the same kind of idea as drawing cards, right? What we would like is that all of the events in our survey are independent events. But when we do surveys, do we sample with replacement or without replacement? When they call up, remember how they're always calling you at dinner time, and annoying you, and wanting to know if you're going to vote for Donald Trump? Do they do sampling with replacement or without replacement? What'd you say?
With replacement?
It's actually without, right? So they have a list of phone numbers. Once they call a number and they get an answer, they mark it out, right? That's without replacement. So technically, we would have dependent events in the sample survey. But later in the semester, we'll talk about the fact that, yeah, it's slightly different. The probability is slightly different, but it's not enough difference to make any real effect on our calculations. So as long as your population is pretty big, and your survey is fairly small relative to the population size, it doesn't matter a whole lot. In fact, it doesn't even matter a whole lot when you have a population of 52 cards. What was our probability of ace on the second draw? Okay, I can't do it that way, right? Because I have to know what happened when we sampled without replacement. I need to know if A1 ace on the first draw. Now you can tell me that probability, right? Probability of ace on the second draw if ace on the first draw. What was that probability? 3 out of 50, 3 out of 51. Right? And then what's the probability of ace on the second draw if ace on the first draw not? That's the one I actually wanted to do. 4 out of 51. As opposed to 4 out of 52 for ace on the first draw. How much different is 4 out of 51 from 4 out of 52? Not much. Right? They're not that big of a difference. So think about it, instead of 52 cards, what if I had, you know, a population of 200,000, like the population of Topeka? If I sample with replacement, without replacement, it's not going to make a huge amount of difference. So we tend to hand wave this problem away when we do sample surveys, as long as we have a big population. But technically, you should be able to tell the difference between independent and dependent samples. Okay? All right, so what I just wrote here, I was careful on how I wrote it, but this is called a conditional probability. Right? So probability of the second thing after knowing what happened on the first thing. That's a conditional probability. Right? So that's a new thing. That's in section 4.3. But what we're going to do is we're going to use this contingency table again to introduce this topic. And we're going to do it first before we have any fancy schmancy formulas. And then when we see the formula, you go, oh yeah, that's what we did. Right? So I want you to compute for me from this table, what's the probability that a smoker exercises? Compute that probability. So here's the data. What's the probability that a smoker exercises? 12 out of 39. Everybody see that? So you will write that this way. The probability that a smoker, I've got two events, smoking and exercising. And when it's said like this, probability that a smoker, that's saying, hey, first they have to be a smoker. They have to meet that condition. So this little vertical line in our probability expression means given or conditioned upon. So red, written as an expression like this, you would read this: probability of being an exerciser given they were a smoker. Okay? Compute that probability for me. Oh, you already did. And what was the numbers? 12 out of 39. Give me that as a decimal. 0.3 what? 3077. Okay? So a little more than 30% of the smokers exercise. Okay? Compute this probability. Among non-smokers, what is probability of exercise? I'm not writing in complete sentences, but you get the idea. Do that one for me. Among non-smokers, what is the probability of exercise? First of all, how do I write it as an expression? You're going to have some homework problems where they just say, here's a sentence, write it as a probability statement. How do I write that?
E given
given
non-smokers.
E given
Non-smokers.
non-smokers. How do I write non-smokers?
Same as.
Well, I have to make up a whole new event. I already have an event for smokers. He did it in the air, right? S, complement. Non-smoker, right? So the probability of being an exerciser given they're a non-smoker. What is that probability? Well, given that they're a non-smoker means, well, they have to be one of these 326 people. So my denominator changes. It's no longer all 365, it's now only 326. So the denominator will be 326, the number of people who meet the conditions. And then the top is the number of exercisers in that row, which is 2 of 6. Okay? Give me that as a decimal.
0.6319.
Point what?
6319.
6319. Okay? Now, before I go on and give you the formula for conditional probability, and then we're going to get from that the multiplication rule that I started over there, is there evidence here from our data that there's an association between smoking and exercising? What does association mean again? Remember we talked about association when we did scatter plots, relationship between two quantitative variables. And we said if certain values of one variable tend to occur more often with certain values of the other. We did shoe size and height. So big shoes tend to happen more often with tall people. What about smoking and exercising? The variables now are categorical. But still, yeses for one tend to occur more often with...
Exercise of non-smokers.
Right. So yeses for exercise tend to occur more often with no's for smoking. Non-smokers, 63% of them exercise. But smokers, only 30%. It's more than double the probability. That's a big difference. So you say, yeah, there is evidence of association here. Now, later in the semester, we'll get a statistical test for whether there's association. For now, we use what's called the eyeball test. We just look at the numbers and say, wow, those are different. So, now with real data, they'll never be exactly the same, but if this one was 0.3077 and this was 0.3122, then you say, yeah, they're pretty close. I don't really see any dependence here. But this is back to being independent-dependent. This says exercising is dependent on smoking. It depends on whether you're a smoker or not as to how likely it is you exercise. So they are dependent events. Okay? Now, let's do the definition of conditional probability. We figured out how to do it using a contingency table just by what made sense, but the probability of E given F, and I'm using E's and F's here not for exercise or anything else, but it's because this is how they list the formula in the book with event E and event F, just generic events. The probability of E given F is the probability that they both occur, which is an AND statement, divided by the probability that the one you condition on has already occurred. Okay? All right, now wait. Let's think about this. You can do this in terms of probabilities, like it's written here, or if you have a contingency table, you can do it with counts. So we did right here. We did the probability of exercising given that they smoke, and we took 12 divided by 39. Now, where did 12 come from? That's the number of people who did both. They were smoking and exercising. Top of the fraction. Smoking and exercising. Right? And then on the bottom was the number 39. Where does that come from? The number who met the condition. So you can do it with number who do these things or probability of doing these things. So let's do it with probability. What's the probability of exercising and smoking? 12 out of 365. What's the probability of being a smoker? 39 out of 365. Now we have a fraction divided by a fraction. How do you do that? You invert and multiply, right? So this is 12 out of 365 times 365 out of 39. And you can do what? So it works with counts, 1239, or probabilities, because the denominators cancel anyway. Right? So this is 12 out of 39. So if you have a contingency table or some other, if you have all of the information of the cross tabulation, then you really don't need this formula to compute a conditional probability. You can just figure it out. But if you don't, sometimes they'll just give you, there'll be a statement like, in a particular town there's 2 newspapers. 40% of the people subscribe to paper number 1. 27% subscribe to paper number 2. And 11% subscribe to both. What's the probability conditional upon? Well, they just gave me, when they say both, they're giving me the top of the fraction, subscribe to paper number 1, right? So you can't always do it with counts. Sometimes all they give you are probabilities. So you have to do it with probabilities. Okay, now, let's come over here to multiplication rule. Take this rule, the definition of conditional probability, and multiply through by the probability of F. You get the probability of F times the probability of E given F equals what? I multiply through by the probability of F. Right? Multiply through. I'm left with probability of E and F. That's called the multiplication rule. In the book, this is written on the left side and this is on the right side. The E's and the F's might be swapped, but don't think of it in terms of memorizing a formula. Think of it in terms of, if I want the probability of 2 events occurring at the same time, then it's the product of one of the events occurring times the other event occurring given that the first one just happened. Right? So, what's the probability that when we sampled with replacement, or without replacement on the cards, what's the probability that both of them got an ace? Probability of ace on the first draw and ace on the second draw. What's that probability?
It's 2 out of 50.
Use the multiplication rule. Multiplication says that the probability of an and is the probability of the first one that's probability of ace on the first draw, times the probability of ace on the second draw, given that the first one occurred. So that's ace on the second draw given ace on the first draw. Now you can fill in numbers. What's the probability of ace on the first draw?
4 out of 50.
4 out of 52. What's the probability of ace on the second draw if the first one was an ace? Given ace. 3 out of 51. Now you multiply those two together, and you have the probability of both of them being aces. Somebody give me this as a decimal. It's some really small probability. That's why a pair of aces in poker is fairly 0.0045. Okay? So about 4 in 1,000 chance. So if we repeated that little thing 1,000 times, 4 of those times, we expect both of them to come up with an ace. Right? Okay, we will see you on Friday. Section 4.2 homework will be due Friday. This is all 4.3 stuff, but since we got it out of the way, we'll spend the time Friday working problems. All right? We'll see you then.